we can rewrite this rational expression using partial fraction decomposition. So multiply everything in this equation by x minus 2x plus 1 to get rid of the denominator. So that's a times x plus 1 plus b times x minus 2. That equals 3. And so we can check some certain conditions that make it easy to solve. You know, if you plug in x equals 2, b is gone. And 2 plus 1 makes 3. So a has to equal 1. It has to be true for all values of x. So it's got to, that means a has to be 1. And then if you do the same thing to make the first term turn into 0, if you plug in x equals -1, then you get -3 times b equals 3, so that means b has to be -1. So we've got our fraction decomposition. It's 1 over x minus 2 plus -1 over x plus 1. So what we have so far in the course when writing power series is we keep relying on this geometric sum, right? If you have a geometric series, you know, a term that keeps, if you have every term is being multiplied by the same common ratio, then it sums up to be this, where x is that common ratio. So we sum it from n equals 0 to infinity. This would be the power series, x to the nth. So we just want to manipulate these fractions until they meet this form, and then we can turn it into a power series. So for this fraction, I'm going to multiply the top and the bottom by, well actually, let's first get them going in the right order. So I'll multiply the top and the bottom by -1. Same thing over here, I'll multiply the top and the bottom by -1. And the reason, oh actually no, I'm going to leave this. I'll show you in just a second why. Because if you do that, then you're going to have a -1 here and a negative sign here. You'll never be able to get the signs to match up. The next thing I'm going to do with this fraction is I'm going to reorder it. And then this fraction over here, I'll take this step now. The trick you need is you're subtracting a -x. And so now all we have to do is, you got a -1 out front, just change this to a minus. And now this meets the form for the sum of a geometric series. This one just needs a little bit of work. Let's multiply the top and the bottom by 1/2. And now this one, once we move the -1/2 out front, this now is in the form of a geometric series. So we're ready to put it in that form. We do the sum from n equals 0 to infinity. For this one, it's a -1/2 is multiplying to the result. So it's -1/2 because we had a coefficient up top, multiplied to x to the nth. But this case, this is our x to the nth. Right? The 1/2 needs to go in. 1/2 x to the nth power. So that's what this is as a power series. And then to write this one as a power series, we don't have any coefficient this time, so it's just -x to the nth power. And then I think it's theorem 6.2 in our textbook tells us that you can just write these as one big happy family, and they've got a proof there. Parentheses. So this is -1/2 times here. This is 1/2 to the nth x to the nth minus -1 to the nth x to the nth. Yeah, so we're able to do that because of theorem 6.2. And then we can clean that up a little bit for WebAssign so that WebAssign doesn't get mad at us. This is -1/2 times 1/2. So let's make that, let's keep the negative sign out front, but that's 1/2 times 1/2, so that's now going to be 1/2 to the n plus 1. And then I'm going to do something with the x to the n's. Look, this is minus a -1/2. You could say that's plus -1 times -1. So I saw when I checked the WebAssign answer, they want n plus 1 here. And that makes sense because if you're minusing by something, you know, like if you have 3 minus 2. That's the same thing as 3 plus negative 1 times 2, right? So that is one way I saw in their answer key, is that they smushed the negative sign in there. I guess they didn't want to have a negative sign. I'm going to put x to the nth on the outside. Factor out an x to the nth. So it should accept this, or you could swap the order. You could say negative 1 to the n plus 1 power minus 1/2 to the n plus 1 power. Just make sure you got the parentheses and make sure you got x to the n multiplying to everything on the outside.